Here are the 5.1 notes. These are quadratic functions. Start with a quick warm-up. So this would be a good time to pause the recording, go ahead and factor. Oops, not what I wanted. Go ahead and factor that x squared minus 24, and then solve the next two quadratics. So hit pause. Once you come back, we will discuss the warm-up. So we recognize, or we want to recognize, that this first one is of the form a squared minus b squared. X squared is a perfect squared. That's the quantity x squared. B squared is a perfect squared. That's 8 squared. We know this is going to factor as x minus 8, x plus 8. If you're having trouble remembering that, go ahead and multiply those back out just to confirm that those middle two linear terms, the minus 8x and the plus 8x, both cancel out. We're going to take it up a notch. This time, as we factor, we're going to keep it set equal to 0. The only way to get x squared is the x times x. I'm going to put that in first. I am now looking for two numbers that I can multiply to get negative 15. Apparently still a little fuzzy here from being sick. Multiply to get negative 15 and add to get that negative 2. That is going to be, well, the 5 times 3 gives me 15 and they're 2 apart. If I want to add them and end up with a negative, the larger has to be negative. So I end up with x minus 5 times x plus 3. Using the zero product property, I know the only way this product can be 0 is if one of the two pieces is 0. So I get either x equals 5 or x equals negative 3. This last one, not as straightforward, but the only way to multiply and get 3x squared is 3x times x. And so now I'm figuring out how I can break up 15 so that I get two numbers that I can combine to get negative 4x. I am settling here on negative 9x plus 5x. That works. I get 3x plus 5 equals 0. To solve, I am subtracting 5 from both sides and then dividing by 3. I am running out of space, so you can crank out that work if you want to see it. And the other one, I get x equals 3. Okay. We want to talk about the basic characteristics of a parabola. And it's interesting that a couple of these things are going to be elaborated on in the next section. So a little bit of a precursor here. Anytime we are graphing a quadratic, that means the highest power is a 2 on any variable. We're going to get this U shape. It's called a parabola. Okay. We have got standard form here in example 1, and I will go through the notes on the left-hand side in a minute. Standard form always looks like this. Y equals ax squared, so something times the x squared term, plus bx, so something times the linear term, plus c, some constant. So in our example here, a equals 1, b equals 4, and c equals 3. You can take a minute to check that out. The first thing this asks is if our parabola opens up or down. I know just by looking at this equation that our parabola opens up. How do I know that? Because my a term is greater than or equal to, sorry, not greater than or equal to, but is greater than 0. It's positive. So because a is positive, If A were negative, both ends would point down. Our y-intercept is where we cross the y-axis. So let's see if I can get my highlighter right here. So here is where we are talking about the y-intercept. If it crosses the y-axis, that means that x is 0. When x is 0, any term that has a 0 in it is going to cancel out. So I'm going to crank this out really quick. Y equals 0 squared plus 4 times 0 plus 3. So y equals 3. My y-intercept here is always 0c. C being my constant in the equation, so my y-intercept here is the point 0.03. There will be some times that they want just the y-coordinate of the intercept. The y-intercept is always a point on the graph, so I tend to write it always as an ordered pair. The x-intercepts, those are going to be the x's that give us y equals 0. And if you think about it, that's what we just did in the warm-up. So I am going to go ahead and factor this. Again, the easy part, x times x, and honestly, the only way to get 3 is to multiply 3 and 1. If these are going to add to give me a positive 4, I got x plus 3 times x plus 1. If x plus 3 equals 0, that means x equals negative 3. And if x plus 1 equals 0, that means that x equals negative 1. So my x-intercepts are the point negative 3, 0, because when I plug in x equals negative 3, I get y equals 0. And the point negative 1, 0. Okay. Our vertex, which, you know, this is great. The notes on the side explain what it is, but not how to find it. Because every single parabola is symmetric. If we take a look at the picture up here, it is cut in half by this axis of symmetry. The axis of symmetry goes through the vertex. The vertex will always be our lowest point if our parabola opens up, or our highest point if the parabola opens down. Okay. Symmetric means that my graph looks exactly the same on both sides. I could fold along that axis of symmetry, and both half of the graphs would lie on top of each other. Which means if I consider what I just found, here are my x-intercepts, negative 3, 0, negative 1, 0. My vertex has to be halfway between those, which means my x has to be negative 2. And we'll talk a little more about how to find that later, if you don't have this factored. If I know the x where the vertex is, I'm going to plug that x back into the equation to find the y that goes with it. Negative 2 squared is positive 4. 4 times negative 2 is minus 8, plus 3. 4 minus 8 is negative 4, plus 3 is negative 1. I get a vertex at negative 2, negative 1. Halfway between these two. My axis of symmetry is the vertical line that goes through my vertex. Vertical lines always have the format x equal, and since it is going through the vertex, x equals negative 2, that's where the vertex is. Now, I'm going to graph the y-intercept. There's my 0, 3. I know that this is symmetric, so 2 to the right, I'm at 3. 2 to the left, I better be at 3. And then I am going to sketch my parabola. And there we go. We're going to work both directions. We're going to write equations from graphs, and we are going to graph from equations. And that is it, but it won't let me shut down the recording.